Liquid nitrogen, LN2, is nitrogen in a liquid state at low temperature. It is produced industrially by fractional distillation of liquid air. It is a colorless, low viscosity liquid that is widely used as a coolant. The diatomic character of the N2 molecule is retained after liquefaction. The weak van der Waals interaction between the N2 molecules results in little interatomic interaction, manifested in its very low boiling point. The temperature of liquid nitrogen can readily be reduced to its freezing point 63 K by placing it in a vacuum chamber pumped by a vacuum pump. Liquid nitrogen's efficiency as a coolant is limited by the fact that it boils immediately on contact with a warmer object, enveloping the object in an insulating layer of nitrogen gas bubbles. This effect, known as the Leidenfrost effect, occurs when any liquid comes in contact with a surface which is significantly hotter than its boiling point. Faster cooling may be obtained by plunging an object into a slush of liquid and solid nitrogen, rather than liquid nitrogen alone. As a cryogenic fluid that rapidly freezes living tissue, its handling and storage require thermal insulation. It can be stored and transported in vacuum flasks, the temperature being held constant at 77 K by slow boiling of the liquid. Depending on the size and design, the holding time of vacuum flasks ranges from a few hours to a few weeks. The development of pressurized super-insulated vacuum vessels has enabled liquid nitrogen to be stored and transported over longer time periods with losses reduced to 2% per day or less. Liquid nitrogen is a compact and readily transported source of dry nitrogen gas, as it does not require pressurization. Further, its ability to maintain temperatures far below the freezing point of water makes it extremely useful in a wide range of applications, primarily as an open-cycle refrigerant, including the culinary use of liquid nitrogen is mentioned in an 1890 recipe book titled Fancy Ices authored by Mrs. Agnes Marshall, but has been employed in more recent times by restaurants in the preparation of frozen desserts, such as ice cream, which can be created within moments at the table because of the speed at which it cools food. The rapidity of chilling also leads to the formation of smaller ice crystals, which provides the dessert with a smoother texture. The technique is employed by chef Heston Blumenthal, who has used it at his restaurant, The Fat Duck, to create frozen dishes such as egg and bacon ice cream. Liquid nitrogen has also become popular in the preparation of cocktails because it can be used to quickly chill glasses of freeze ingredients. It is also added to drinks to create a smoky effect, which occurs as tiny droplets of the liquid nitrogen come into contact with the surrounding air, condensing the vapor that is naturally present. Nitrogen was first liquefied at the Jagiellonian University on 15 April 1883 by Polish physicists Zygmunt Wroblewski and Karol Olszewski. Because the liquid-to-gas expansion ratio of nitrogen is 1:694 at 20 degrees Celsius, a tremendous amount of force can be generated if liquid nitrogen is vaporized in an enclosed space. In an incident on January 12, 2006 at Texas A&M University, the pressure relief devices of a tank of liquid nitrogen were malfunctioning and later sealed. As a result of the subsequent pressure buildup, the tank failed catastrophically. The force of the explosion was sufficient to propel the tank through the ceiling immediately above it, shatter a reinforced concrete beam immediately below it, and blow the walls of the laboratory 0.1 to 0.2 meters off their foundations. Because of its extremely low temperature, careless handling of liquid nitrogen and any objects cooled by it may result in cold burns. In that case, special gloves should be used while handling. However, a small splash or even pouring down skin will not burn immediately because of the Leidenfrost effect. The evaporating gas thermally insulates to some extent, like touching a hot element very briefly with a wet finger. If the liquid nitrogen manages to pool anywhere, it will burn severely. As liquid nitrogen evaporates, it reduces the oxygen concentration in the air and can act as an asphyxiant, especially in confined spaces. Nitrogen is odorless, colorless, and tasteless and may produce asphyxia without any sensation or prior warning. Oxygen sensors are sometimes used as a safety precaution when working with liquid nitrogen to alert workers of gas spills into a confined space. Vessels containing liquid nitrogen can condense oxygen from air. The liquid in such a vessel becomes increasingly enriched in oxygen as the nitrogen evaporates, and can cause violent oxidation of organic material. Ingestion of liquid nitrogen can cause severe internal damage due to freezing of the tissues which come in contact with it and to the volume of gaseous nitrogen evolved as the liquid is warmed by body heat. In 1997, a physics student demonstrating the